Here's a problem that I found on the 2015 University of Waterloo Bernoulli Trials competition. This competition was aimed at all undergrads, so in theory, anyone, even from first year, should be able to attempt these problems. They might be a little bit challenging for a first year, but they're accessible. And I found this to be a fun little reminder of number theory, modular arithmetic. So let's take a look at how we might approach this. So the Bernoulli trials are all true or false. And this one asks or states that the smallest positive integer x, such that 7 to the power of x is congruent to 1 mod 2015, is larger than 100. So is that true or false? I would encourage you to give this a try yourself and see how your mind tosses up ideas and how you might bat them away or grow them into a solution here. For me, it took me quite a while. I'm not much of a number theorist myself, but it was nice to feel the old gears starting to turn a little bit. And I finally struck on inspiration a little later. So the first thing that we might consider is that this is an exponential congruence in modular arithmetic that's congruent to 1. So we probably are tempted to use something like Fermat's little theorem or Euler's theorem. So let me just state Euler's theorem. It says that a to the power of the quotient of n is congruent to 1 mod n when the GCD of A and N is 1. So this is kind of an upgrade of Fermat's theorem, which says that A to the P minus 1 is congruent to 1 mod P when P is prime. So can we use this result? Okay, so in order to use this result, we got to compute the totient function. So that means probably want to factor 2015 in terms of its prime factors. So after some playing around with it, so first of all, we can see that it's definitely divisible by 5. And then the search for primes is a little bit more annoying, but it turns out that you can factor this into 5 times 13 times 31. Okay, so that allows us to calculate the totient function of 2015, which is 2015 times 1 minus 1 over 5 times 1 minus 1 over 13 times 1 minus 1 over 31. We could calculate this, but I'm more of an analyst, so I'm going to use the fact that these are going to be larger than zero point 0.9, and this is going to be larger than zero point 0.9. So, in other words, this whole thing is going to be larger than 1,000, and that unfortunately doesn't help us solve our problem. So notice that Euler's theorem doesn't say that the totient function is the least such integer. It just guarantees that that is, well, it's greater than or equal to the least one. This is no good because it doesn't say tell us least. So that would have been good if that was less than 100, because then we know that the statement must be false. But unfortunately, since this gives us a very large number, we can't guarantee that the statement's false or true. So we seem to be a little bit stuck again, and this is where I got stuck. How do we proceed from here? Another thought that occurred to me was to use the fact that we can decompose n. So we can use our factorization of 2015, and instead try to consider all the x's such that 7 is congruent to 1 mod all of its prime factors. So mod 5, 7 to the power x is congruent to 1 mod 13, and 7 to the power of x is congruent to 1 mod 31. The insight here is that if I can find a single positive integer x such that all of these are true simultaneously, then it must be true that 7 to the power of x is congruent to 1 mod 2015. So now we can actually apply Fermat's little theorem here to get that x is congruent to 0 mod 4 from the first one. From the second one, x is congruent to 0 mod 12, and x is congruent to 0 mod 30. And luckily, since we're considering homogeneous equations here, we can actually just take the least common multiple of each of these mods. So the least common multiple of 4, 12, and 30 turns out to be 60. So in fact, that tells us that x equals 60 should work. In particular, that x satisfies all of these equations simultaneously. So 5 divides 7 to the power 60 minus 1, and 13 divides 7 to the power 60 minus 1, and 31 divides 7 to the power of 60 minus 1, but 5, uh, 13, and 31 are all distinct primes. So 2015 divides 7 to the 60 minus 1, and that means that 7 to the power of 60 is congruent to 1 mod 2015. Okay, so all that work tells us that we can go back up here and say, in fact, this statement is false. We found a smaller number, x, than 100 that makes this congruence work. I find that doing fun problems like this helps you sharpen up your intuition and your understanding of concepts in any topic. Even just struggling with the problem and not necessarily making progress can help you learn stuff in a much deeper way than just passively listening to lectures or doing textbook problems.